Jai Jagannath. Welcome to More Physics. So today is lecture number. Today is lecture number 4, chapter 21. So same chapter, that is the electric field and electric charge we are discussing. So in the last class we had discussed about the electric field and how can you find the electric field's intensity, and we have also solved some numericals. So today we will discuss electric dipole. Electric dipole. So what is electric dipole? You see, electric dipole. So here electric comes from the word I have already told. This is electron. Electron is which particle? Charged particle. Electron is a charged particle. Di means what? Di means two. Pole. Pole means polarity, either positive and negative. So from this name we can define what is electric dipole. So electric dipole is two equal and opposite charge separated by a very small distance apart is called electric dipole. Suppose you see, this is here, this is a charge minus q, this is plus q charge. So these two charges are of equal magnitude and opposite sign and separated by very small distance. So this distance is very small actually. So it is seen bigger, but actually the distance between these two charges is very small, and these two equal and opposite charges separated by a small distance apart forms an electric dipole. Clear? So you can write the definition. What is electric dipole? Two equal and opposite, two equal and opposite charge separated by very small distance apart is called electric dipole. So so if I will take actually zoom of this electric dipole, this is minus q, this is plus q. So I am taking actually bigger size, but practically the distance between these two charges is very small, and join a line with the center of these two charges. So now this line is called here axial line. So what is axial line? It is the line joining between the center of these two charges, and the middle point of this dipole is called center of dipole. So here O is the center of dipole. So this O is center of dipole, and a line which is perpendicular to the axial line and passing through the center of dipole is called equatorial line. So this is called equatorial line. So now, so this is about the electric dipole. Then what is the dipole distance? This minus q, this plus q is separated by a distance, let us say d. So this d is called dipole distance. D is called dipole distance. Then what is electric dipole moment? So electric dipole moment. So if I write P, P is called electric dipole moment. So what is electric dipole moment? It is nothing but product of either of the charge, that is Q, into their separation distance, that is D. So this is called electric dipole moment. So now electric dipole moment is a vector quantity. If it is a vector quantity, definitely it has a direction. So direction of electric dipole moment vector, that is P vector, is always from negative to positive. That is, this is, you see, this is minus q charge, this is plus q charge. So the electric dipole moment direction is from minus q to plus q, lies along the axial line. So direction of dipole moment is always from negative to positive charge, negative to positive charge along axial line. Then what is the unit of dipole moment? Unit of dipole moment. So you see, charge into distance, that is Coulomb meter. So this is the unit of dipole moment. Then what is the dimensional formula of dipole moment? Dimensional formula of dipole moment. You see, it is charge into distance. Charge q is equal to it, that is a ampere, time t, into distance. Distance is l. So there is no mass. So m naught, l1, at. So this is the dimensional formula. Q is equal to it, at, then distance. Okay. So this is the dimensional formula of dipole moment. Next, we will find, question may come, derive the electric field intensity due to a dipole, on the axial point, So this is a derivation. Actually, this is a small derivation. Electric field intensity you have to find due to a dipole on the axial line. So you see, suppose this is your minus q, this is plus q, and the dipole distance. So this is the center of dipole, and the dipole distance is d. So from the, let us say this point is okay. So this distance minus q to center, it is d by 2, and center to this plus q is also d by 2, because the total distance is d. And this is which line? This is axial line. So I want to find the electric field intensity at point, say A, at point A. So A is which point? A is point lying on the axial line of the dipole. So first we have to calculate, you have to use superposition theorem. So first you calculate electric field intensity at A point, due to this minus q charge. So I can write it is EA minus, that is EA minus is nothing but electric field due to minus q charge. At which point? At A point, is equal to, suppose this A point is at r distance from the center of dipole. This A and O point distance is r. So what is electric field intensity at A point due to minus q charge? So you know electric field intensity formula is equal to K charge. What is the charge? Q by the distance between charge and the point A. So here it is d by 2, here it is r. So total distance is r plus d by 2 whole square. So this is the electric field intensity at A point due to minus q charge. And you have to find what is the direction. So to find the direction, you know there are two methods you can find. For negative charge, electric field is always towards it. So electric field at any point is always towards the negative charge. So since it is minus q, so direction of electric field at A point is towards negative side. So this is your what? EA minus. Or you know what is electric field intensity? It is the force per unit positive test charge. So if I will keep a plus 1 charge here, this plus 1 will be attracted by this negative charge along this direction. So that's why this is the direction of the electric field due to negative charge. So I can write the electric field direction is towards left. Similarly, find out the electric field intensity at A point due to plus Q charge. So that is equal to electric field intensity at A point due to plus Q charge is equal to what? So here charge value is Q. So KQ divided by distance between this to this. So the total distance from O to A is equal to R. So from R you subtract this distance d by 2. So you will get distance from this point to this point, that is equal to R minus d by 2 whole square. And since it is positive charge, you know electric field is always away from a positive charge body. So since this is positive and we have kept here plus 1 charge, so now this plus q will repel this plus 1 along this direction. So this is the direction of electric field intensity due to positive charge. So now what we will do? We will find the total electric field intensity at which point? At A point. So here what is the direction of EA plus? Right side. Now you compare which value is more, this value or this value. So here denominator is less comparing to this. So if denominator is less, definitely this value EA plus is greater than EA minus. So I can write EA plus is greater than EA minus. So EA plus is towards right side, EA minus is towards left side. So they are opposite and EA plus is greater than EA minus. So what is the net electric field intensity? So net electric field intensity at A point is equal to, I can write it is EA, which is equal to, so this is EA plus is more than EA minus. So net is equal to EA plus minus EA minus. That is equal to, what is the value of electric field intensity due to positive charge? So this value KQ divided by R minus d by 2 whole square, and minus this value, that is KQ by R plus d by 2 whole square. So now if we'll take the sum, take common KQ, and what is the LCM? A minus B whole square by A into A plus B whole square is equal to A square minus B square whole square. So that is R square minus D by 2 whole square, that is D square by 4 whole to the power square. And so here KQ common, so just R plus D by 2 whole square minus R minus D by 2 whole square. So that implied electric field intensity at A point is equal to KQ, and you know A plus B whole square minus A minus B whole square is equal to what? 4 into AB. So that is equal to 4A. A is equal to what? R. B is equal to what? D by 2 divided by this value, R square minus D square by 4 whole square. So that is equal to 2, 4. 2 cancel. So you will get K 2, this 2, this 4. So 2. So 2K Q into D into R divided by R square minus D square by 4 whole square. This is the electric field intensity at A. So, and you know the what is electric dipole moment? Electric dipole moment is equal to charge into distance of separation, Q into D. So in place of Q into D, I will write the dipole moment P into R divided by R square minus D square by 4 whole square. This is the electric field intensity at which point? At axial point due to a dipole. So I am writing within the box. Box means you have to store this in your memory box. Okay, because this is important. Now you see, what is the definition of dipole distance? So definition of dipole distance is the separation distance is very small. So that means in general, the separation distance, that is D, is very small. So we can say this distance, separation distance d is very, very small than r. If d is very, very small than r, then d square by 4 is also very, very small than r square. So we can neglect this d square by 4 comparing to r square. Comparing to r square. So neglecting d square by 4 comparing to r square, we have electric field intensity at axial point. Electric field intensity at axial point is equal to 2 kp. Here r, so d square by 4 neglect, so it will be 0, so it will tends to 0. So r square to the power 2, that is r to the power 4, here r, so that means 2 kp by r cube. So this is the electric field intensity at axial point. So and what is the direction of this electric field intensity at axial point? So direction of electric field intensity at axial point is towards right. Towards right means what is the direction of the dipole moment? Dipole moment direction is minus q to plus q along the line from minus q to plus q. So since we are getting net electric field intensity is towards right, so that's why direction of electric field intensity due at axial point due to a dipole is along the direction of dipole moment. Is along the direction of the dipole moment. Now next the derivation, small derivation. Derive the electric field intensity due to dipole on equatorial line. Now you see, this is minus q, this is plus q. So this is the equatorial line. This is equatorial line, and the distance of separation between two dipoles is d, and this A point, which is lying on the equatorial line, is at r distance from the center of the dipole. So we have to find what is the electric field intensity at A point. So what we'll do? So first we will calculate electric field intensity at A point due to minus q charge. So I am writing here minus. So this is what actually electric field at A due to which charge? Due to negative charge, minus q charge. So that is equal to, again formula is k, charge is q by distance square. What is distance here? So minus q charge to this A point. So this is d by 2, this is r. So this distance is equal to what? D by 2 whole square plus r square root. But it is kq by distance square. So I am writing this is the value of electric field intensity at which point? A point due to minus q charge. And what is the direction? Direction is c. This is negative charge. So if I will keep a plus 1 charge here, this negative will attract this plus 1 charge along this direction. So this is the direction of what? Electric field intensity at A due to minus charge. So I can write here along, just give a name here. This is, let us say, B. This point is C. So along AB line. Similarly, find out electric field intensity at A point due to charge at C, that is plus q charge. So that is taken to be electric field intensity at A due to plus charge. So I am writing plus. So that is equal to, what is the value? Q. So kq by square of the distance. Square of the distance is the same. That is here r, here also d by 2. So that is d square, d by 2 whole square plus r square. And what is the direction? This is positive charge. So always electric field intensity is away from a positively charged body. So if you see, or I can say if we'll keep plus 1 charge here, so this plus q will repel this plus 1 along this direction. So this is the direction of electric field intensity at A due to positive charge. So now just draw a horizontal line here, and if this angle is alpha, this angle is alpha. If this, so this is isosceles triangle. If this is alpha, this is also alpha. If this is alpha, this angle is also alpha. Then what we'll do? We will add. We will find the total electric field intensity at A point due to dipole. So that means electric field intensity at A is equal to electric field intensity at A due to negative charge vector plus electric field intensity at A due to positive charge vector. So you will add these two vector. So EA plus, what is the direction of EA plus? Along C to A line. So I am writing here along CA line. So total electric field intensity is equal to sum of these two vectors. Now you know there are two vectors, and what is the angle between these two vectors? 2 alpha. So we can add vectorially by using which method? Using component method. So you see, what is the x component of this EA vector, EA plus vector? So s component will lie along this direction. So what is the s component of this vector? EA cos alpha. And what is s component of this EA minus vector? Again EA minus cos alpha. So both s component will lie along this direction. And you see here magnitude of EA minus and the magnitude of EA plus both are same. So I can write EA minus is equal to EA plus. Now if I will calculate the y component, so y component. So here you see what is the y component of EA minus vector. So this will lie in which direction? Negative direction. What is the value? EA minus sin alpha. And what is the y component of this vector EA plus? So that is, it will lie along vertical y direction, which is equal to EA plus sin alpha. And these two vertical component magnitude are same, direction is opposite, so they will be cancelled. Only which component will remain? Only x component. So we have to find the total electric field intensity. So here we can write the y components of EA plus and EA minus will cancel. So only x component will be there. So now we can say total electric field intensity at A is due to the s component of these two vectors. So what is the s component of individual vector? EA plus cos alpha plus EA minus cos alpha. Of course, these two vectors are same. What is EA plus or EA minus? That is KQ by R square plus D square by 4. So this is your EA plus or EA minus value. Then what is cos alpha? You see, this is alpha. This is your right angle triangle. This is your right angle triangle. Cos alpha is equal to base by hypotenuse. Base is D by 2. Hypotenuse is this distance. What is the distance? So distance is D square by 4 plus R square square root. So this is the total electric field intensity at which point? A point. And this A point is lying on which line? Equatorial line. On equatorial line. So that implied EA is equal to, you see, then EA cos alpha. Yes, this is EA cos alpha. Similarly, this is EA minus cos alpha. Both are same. So the total electric field intensity is equal to 2 times of this value. So here 2 cancel. You are getting K into QD divided by R square plus D square by 4 whole to the power 3 by 2. 3 by 2. But you know, charge into distance is nothing but your dipole moment P. Kp by R square plus D square by 4 to the power 3 by 2. So we know generally the dipole distance d is very small than r. So we can neglect d square by 4 is very small than r square. So we can neglect this d square by 4 comparing to r square. So if you neglect, let us say it is 0, then it is kp by r square to the power 3 by 2. 2 cancel. So electric field intensity at a point, that is a is which point? Equatorial point is equal to kp by r cube. And what is the direction of the electric field intensity at equatorial point? You see, direction is, so what is the direction of the electric field intensity? What is the direction of the dipole moment? The direction of the dipole moment is minus q2 plus q. But what is the direction of electric field intensity at a point? It is just opposite to that of dipole moment. So we can write the direction of electric field intensity at equatorial point is opposite to that of dipole moment direction of dipole moment. So so this is about the, so we derived the electric field intensity at the axial point and also at equatorial point. So next is your force and torque on an electric dipole. Force and torque on an electric dipole. So now see, suppose you take a uniform electric field. Uniform electric field is represented by the same line of equal magnitude, same direction with equal space. This is called uniform electric field. Inside the uniform electric field, take a dipole. Let us say this is a dipole, this is minus q, this is plus q. So this is an electric dipole. This is the center of dipole. So here what will happen? The electric field strength is E. So we can write here, you see, let us say the E is the uniform electric field strength. Now, if I will bring, when a charged particle is brought inside an electric field, what will happen? That charged particle will experience a force. And if the charge is positive, the direction of the force is along the direction of E. If the charge is negative, the direction of force is opposite to that of E. So that means inside this electric field, so there is a charge plus Q. So this plus Q will experience a force of magnitude Q into E along the direction of electric field. And this minus Q charge will experience a force of same magnitude, that is QE, but in opposite to that of E. Now see, these two forces on the dipole are of equal magnitude and are opposite, and they are acting in two different lines, so they form a couple. So these two forces, they will form a couple. And what is the effect of the couple? Couple will produce a rotational motion. So now due to these two forces, so this dipole will try to rotate. And for rotational motion, torque is responsible. So we will derive the torque. So what is torque? Torque is equal to the force into perpendicular distance between the line of action of force. You see, This force is acting along this line, and this force is acting along this line. So this is force. And what is the perpendicular distance? The perpendicular distance is equal to, so if I will extend this is the perpendicular distance. This is the perpendicular distance. Let us say this is A point, this is B point, this is your C point. So now see, so I can say torque is equal to force into perpendicular distance, that is equal to force into, what is perpendicular distance in this figure? It is BC. And what is the value of BC? Now see, you see, what is the dipole moment? Dipole moment is equal to, what is the direction of the dipole moment? Minus q to plus q. So this is the direction of the dipole moment, minus q to plus q. And this is the direction of the electric field. So this is dipole moment vector, this is electric field vector. The angle between these two vector is equal to, say, theta. If this angle is theta, this angle is also theta. So now, what is the distance? What is the dipole distance? This dipole distance is AB. So here, AB is the dipole distance, which is generally taken D. And what is the dipole moment vector? What is the magnitude of the dipole moment? So product of charge into separation distance, that is Q into D. So now, what is the value of F? What is the, so now we will find the torque. Now we will find the value of torque. So torque is equal to F into perpendicular distance, that is B. F is equal to QE into BC. So what is BC? In this right angle triangle, sin theta is equal to BC by AB. Sin theta is equal to BC by AB. So BC is equal to what? AB sin theta. So that is equal to QE. What is AB? AB is the distance, dipole distance, that is D sin theta. That is equal to Q D into E into sin theta. So QD is nothing but what? Dipole moment, that is P. So PE sin theta is the torque value. So this is in which form? Magnitude. Torque is equal to P sin theta. But we know torque is a vector quantity. Torque is a vector quantity. So if I will write torque in vector form, so I will write torque is equal to P cross E. P cross E. So what is the magnitude of torque? The P is sin theta. So what is theta? Theta is the angle between which vector? P vector, dipole moment vector, and electric field vector. So this is the angle between P vector and E vector. And how will you find the direction of the torque? So direction of torque can be found using vector rule. That is right hand rule. So according to the right hand rule, you see, so here, what is the direction of P vector? P vector direction is this. And what is the direction of the electric field vector? Electric field vector direction is this. So now this angle is theta. So now according to the right hand thumb's rule, if here P is the first vector, E is the second vector, keep your forefinger on P vector, that is first vector, and rotate the first vector towards the second vector. So when you are rotating P vector towards E, the thumb will give the direction, that is inward. That is, the torque is perpendicular to this board and it is inward. So direction torque can be found using right hand rule, and particularly in this case, torque is inward, that is perpendicular to board, and inward. Okay, so you know the rule. Torque is perpendicular to both P vector and E vector. So here P vector, E vector is lying on the board. So torque is perpendicular to the board, and according to the right hand rule, it is inward. And you know, according to the circular motion concept, if the direction is inward, if the direction thumb is inward, then the four fingers will give the direction of the rotation. So here direction of the rotation is clockwise. So here the dipole will rotate in which direction? Clockwise. So I think it is clear. So this is the expression of the torque. Now you see, but what is the net force on the dipole? What is the net force on the dipole? You see, this is the dipole. So this is minus q, this is plus q. Here electric field applies a force of QE towards right. Here electric field applies a force of QE towards left. So since this is dipole, if I'll take the free body diagram of this dipole, so one force is towards right, another force is towards left. So net force is equal to what? 0. So net force on a dipole is always 0. So if net force is always 0, then dipole remains in which equilibrium? Translational equilibrium. Translational equilibrium. We know in mechanics, in laws of motion, we have read if the net force on a body is 0, then it will remain in linear equilibrium or translational equilibrium. But if the net torque will be 0, then body will remain in rotational equilibrium. So dipole is always remains in which equilibrium? Translational equilibrium. You have to remember. So next we will discuss case 1. Different case. Case 1. Suppose theta is equal to 90 degree or 270 degree. Theta is the angle between what? Dipole moment and electric field vector. So if theta is equal to 90 degree or 270 degree, what do you mean by that? Suppose this is an electric field. This is an electric field. You bring a dipole, here minus q, here plus q. So this minus q to plus q is the direction of the dipole moment, and this is the direction of the electric field. So here the angle between P vector and E vector is equal to, if you take the reference E vector, this is your P vector. So you can say the angle between E and P is equal to what? 270 degree. But if I will keep here minus q, here plus q, this is the direction of the dipole moment. So here P is upward, E is horizontal. So if we measure the angle in anticlockwise direction with taking E as the reference, so here theta is equal to 90 degree. So in this case, if we will keep a dipole perpendicular to the direction of electric field, what will be the torque? Torque will be P sin theta. So here theta is 90 degree or 270 degree. So that means the torque magnitude will be P. So it is maximum torque. It is maximum torque. So under what condition a dipole will experience a maximum torque? When the dipole is perpendicular to the direction of the next. Case 2. Case 2. So case 2 is when theta is equal to 0 degree, that is called parallel, or theta is equal to 180 degree, that is anti-parallel. Anti-parallel. So here theta, so that means what? That means suppose theta is equal to 0 degree. Suppose this is your uniform electric field. Theta 0 means you bring a dipole. So this is minus q, this is plus q, this is the direction of the dipole moment. So here P vector and E vector both are parallel, so theta is equal to 0. So if theta is equal to 0, we know the dipole, always net force on the dipole is equal to 0, always. You see, here plus q will experience a force QE towards right. Here minus q will experience a force of QE towards left. So the net force on the dipole is 0. Then what is the torque? So torque is nothing but P sin theta. So here theta is angle between P and E vector. Theta is equal to 0. So torque is equal to 0. Torque is equal to 0. So here force is 0. Torque is 0. So it is called translational and rotational equilibrium. Both will be so the total dipole is in translational equilibrium as well as rotational equilibrium, because net torque 0, net force is equal to 0. Then it is also called stable equilibrium. It is also called stable equilibrium. Why it is called stable equilibrium? I am explaining this. You see. Suppose this is the dipole. Initially the dipole is in equilibrium position. So now I will try to rotate this dipole in which direction? In anti-clockwise direction. So what will happen? Suppose so after some rotation, this is plus q, this is minus q. So when I will rotate by some angle theta, so this q will experience a force towards right and minus q will experience a force towards left, that is qe. So same magnitude, so opposite sign. So if I will try to rotate the dipole in anti-clockwise direction, now a torque will be produced due to this QE force, and that torque will try to bring the dipole again to its initial position. So you see, so this is initially this is the electric field and this is the dipole. So here if I will try to bring the dipole, I will rotate the dipole in which direction? Anti-clockwise direction. Dipole will come to here. So again here QE force, here QE force. So these two forces will develop, which will try to rotate the dipole to bring the dipole in its original position. That's why it is called stable equilibrium. What is stable equilibrium? You see, just example. What is the stable equilibrium? Suppose this is a cup. If this is a ball, you will keep in the base and just give a small jerk. This ball will move upward, again it will come downward, so finally it will come to its original position. So that is called stable equilibrium. Here also, when theta is equal to 0 degree, then dipole will remain in stable equilibrium. Dipole will remain in stable equilibrium. So next, when theta is equal to 180 degree, what will happen? When theta is equal to 180 degree, suppose this is the direction of the electric field and you take a dipole. Let us say this is plus q, this is minus q. So this is your dipole moment vector. So here electric field is towards right, dipole moment is towards left, theta is equal to 180 degree. So here net force again always 0. Then what is torque? Torque is equal to P sine theta. Theta is equal to 180. So again torque is equal to 0. But in this case, what will happen? If I will try to rotate, you see. So if suppose this is dipole, so minus q plus q. I will try to rotate the dipole. This minus q will be rotated in anti-clockwise direction, plus q will be rotated in anti-clockwise direction. So if I will try to rotate this dipole in anti-clockwise direction, what will happen? You see. So here after some time minus q will come to here, plus q will come to here. This plus q will experience a force along the direction of E vector, that is QE, and this minus q will experience a force of magnitude QE opposite to that of electric field. Now you are trying to rotate in which direction? Anti-clockwise direction. After that, a torque will be developed by this QE and this QE, which will again rotate the dipole in same direction as that of initial rotation. So we have already rotated this dipole in which direction? Anti-clockwise direction. So now after rotation a torque will be developed. That torque will again rotate this dipole in same direction. That means this dipole will never come back to its original position. So that's why it is called unstable equilibrium. That's why it is called unstable equilibrium. So under what condition the dipole is said to be stable equilibrium? If theta is equal to 0 degree. Stable equilibrium condition, theta is equal to 0 degree. Unstable equilibrium condition, theta is equal to 180 degree. Then potential energy. So this is also a small derivation. Potential energy of an electric dipole. Potential energy of an electric dipole. So suppose you see, let us say this is the electric field, uniform electric field. So this is the direction of the electric field. So now I will take a dipole. This is minus q, this is plus q. This is the direction of the dipole moment p vector. And initially the angle between dipole moment vector and electric field vector is say theta 1. So here the dipole will experience a force of QE along the direction of E, and here minus Q will experience a force of QE opposite to that of E. So now if this dipole is rotated by some angle in anti-clockwise direction, it will come to this position. So I am trying to rotate this dipole in which direction? Anti-clockwise direction. What was the initial angular position? What is the initial angle between dipole moment electric field vector? Theta 1. Now it is theta 2. So you are rotating this dipole from theta 1 angle to theta 2 angle. So in this process, the external agent is doing some work. Or you can say, you see, so here, what is the direction of the torque? So in the initial case, so this is QE, this is QE. So these two forces will produce a torque in which direction? Clockwise direction. But we have to rotate this dipole in which direction? Anti-clockwise direction. So that means against to the torque, we have to apply some external torque so that dipole will move from theta 1 to theta 2. So when you are rotating the dipole against to the torque, the amount of work done will be stored in the dipole in the form of potential energy. So in the mechanics, suppose this is a body. This body is lying in the ground. So I want to raise this body to certain height. Against which force? Against gravitational force. So the amount of work done will be stored in the body in the form of potential energy. So here same case. So here, torque already is there in which direction? Electromagnetic torque. The torque due to dipole is in clockwise direction, but we want to rotate the dipole in anti-clockwise direction. So we have to do some work. So that work will be stored in the body in the form of potential energy. So now work done by electrostatic force, is equal to negative of work done by the external force. Just like if I will raise the body in so I am is the external agent. I am doing the positive work and gravitational force is doing negative work. So we have to first we will find work done by electrostatic force. So what is the work done by electrostatic force? Work done by electrostatic force is equal to dW, integration of dW from 0 to W. So that is equal to, in linear case work done is equal to F dot ds. In rotational case work done is equal to tau dot d theta. So this is the expression of the work done in rotational case. So initial angle is theta 1, final angle is theta 2. So that is equal to tau dot d theta. Here electrostatic force is the here torque. So here the torque is in clockwise direction. Electrical, that is torque due to dipole, is in clockwise direction. Rotation is in anti-clockwise direction. So theta and torque are opposite. So here you have to take tau d theta cos 180. A dot b is equal to AB cos theta. So here theta is equal to 180 degree, because the torque due to dipole is in clockwise, rotation is just opposite, that is anti-clockwise. So theta is equal to 180 degree. So integrate this from theta 1 to theta 2. So what is the value of torque? Torque is equal to P E sin theta d theta cos 180 is minus, so theta 1 to theta 2. So that is equal to minus P sin theta. So what is the integration of sin theta? It is minus cos theta. Minus cos theta, limit theta 1 to theta 2. So minus minus plus, that is P cos theta 2 minus cos theta 1. So this is what? This is work done by electrostatic force. Electrostatic force. Then what is work done by external agent? Work done by external agent or external force is equal to what? It is negative of work done by the electrostatic force. Just like work done by the gravitational force is negative of work done by the external agent, we have discussed in the mechanics chapter. So here work done by external force is equal to negative of work done by the electrostatic force. So that is equal to minus, okay. So this is P cos theta 2 minus this. So which is equal to work done by the electrostatic force. So work done by the external force is equal to what? Minus of this. So minus P cos theta 2 minus cos theta 1. But we know work done by the external force will increase the potential energy. So potential energy increases means final potential energy minus initial potential energy is equal to change in potential energy, which is equal to work done by the external force. But work done by the external force is equal to this much. So this is equal to change in potential energy. Change is always final minus initial. So you have to remember this formula. So keep in your memory box. So this is the change in potential energy. So now let us assume, let initially theta 1 is equal to 90 degree. Initially the dipole was making 90 degree with the electric field. So let theta 1 is equal to 90 degree. If theta 1 is equal to 90 degree, then what is potential energy? Initial potential energy cos 90, that is 0. So that implied potential energy when theta 1 is equal to 90 degree is equal to 0. So now u theta 2, that the final potential energy is equal to minus Pe cos theta 2. Or in general, if the body moves to a new angle theta, then potential energy is equal to minus Pe cos theta. So this is the expression of the potential energy. But P is a vector, E is a vector, Pe cos theta is nothing but P vector dot E vector. Dot product of P is equal to P cos theta. Here minus, here minus. So this is the expression of potential energy of a dipole. So how will you remember? Potential energy, first letter is P, energy first letter is E. So just give a minus P dot E, that is potential energy formula. So now we will compare the various case, that is case 1, case 1, case 2, case 3. So you see case 1, let theta is equal to 90 degree. Theta 90 degree means electric field and dipole they are perpendicular to each other. If theta is equal to 90 degree, we know for electric dipole always net force is equal to 0, and the net what is that net torque? What is the torque? Torque is equal to P sin theta. Theta is equal to 90. So sin 90 is the maximum. So here you will get maximum torque. And what is the potential energy? Potential energy in this case, potential energy is equal to minus P cos theta. Theta is equal to what? 90. Cos 90 is equal to 0. So potential energy is 0. Come to case 2. Case 2, here theta is equal to 0 degree. Theta 0 degree means the electric field vector and the dipole vector both are parallel to each other. P vector and E vector both are, P vector is parallel to E vector. So here theta is equal to 0 degree. Theta 0 degree means net force is always 0 every time. And here what is the torque? Torque is equal to P sin theta. Theta is 0. So torque is equal to 0. So torque is equal to 0. Then what is potential energy? Potential energy is equal to minus P cos theta. Theta is 0. That is minus P. So which is equal to minimum. So what do you mean by minimum potential energy? If anybody possesses minimum potential energy, then it is called stable equilibrium. For stable equilibrium, potential energy is always minimum. Suppose a rain is falling from the top. So always rain will fall to what? Will try. The rain will fall to the ground means ground has minimum potential energy. So when a raindrop is at the ground level, it is more stable. So if anybody having minimum potential energy, that is called stable equilibrium. Case 3. So here electric field. So here let us say this is plus Q, this is minus Q. So here dipole P vector is opposite to electric field vector. So theta is equal to 180 degree. So if theta is equal to 180 degree, net force always 0. Then what is the torque? Torque is equal to P sin theta. Theta is equal to 180. So torque is also 0. Then what is potential energy? Potential energy is nothing but minus P cos theta. Theta is 180. Cos 180 is minus 1. Minus into minus plus. So it is plus P. So this potential energy is maximum. And we know if the potential energy is maximum, then it is which equilibrium? Unstable equilibrium. Unstable equilibrium. Just like suppose this is the ground level. This is a cup. If you keep a ball here, it will always try to move to downward. So this is called unstable equilibrium. But this is a cup. This is the ground level. If a body is at the base of this cup, so here potential energy is minimum, it is more stable. Here potential energy is maximum, it is solve. Let us solve example 21.3 of University Physics book. So here you see, let us say this is an electric field. This is an uniform electric field of strength given 5 into 10 to the power 5 Newton per Coulomb. And a dipole is there. So here it is minus Q charge. Here it is minus Q charge. Here it is plus q charge. So this is a negative charge, this is positive charge. So here the angle, this angle is 45 degree, and this is the direction of the electric field. And what is the separation distance? Separation distance is given d. D is the separation distance, which is equal to 0.125 nanometer. Nano is nothing but 10 to the power minus 9 meter. Here charge is given 1.6 10 to the power minus 19 coulomb, and in uniform electric field strength is given 5 into 10 to the power 5 Newton per coulomb. So from this we can find what is the dipole moment. So dipole moment is a product of charge into separation distance. Q is 1.6 10 to the power minus 19. Distance is 0.125 into 10 to the power minus 9. So if we'll multiply, I think it will come 2 into 10 to the power minus 29 coulomb meter. This is the dipole moment. So now here what is the angle theta? Theta is the angle between which vector? P vector and electric field vector. Here you see what is the direction of the P vector. So here it is minus q, here it is plus q. So direction of the dipole moment is always from negative to positive, and this is the direction of the electric field vector. So this angle is our theta. So theta is equal to 135 degree. Theta, so theta is the minimum angle between P vector and E vector. Minimum angle is equal to 135 degree. So first bit, what is the dipole moment? So first bit we have solved. So this is your first bit. Dipole moment is equal to 2 into 10 to the minus 29 coulomb meter. Second bit, what is the torque? So torque formula is equal to what? P sin theta. So that is P is equal to 2 into 10 to the power minus 29. E, what is the value of E? 5 into 10 to the power 5 into sin theta. Theta is equal to 135 degree. So if we'll, this is 145 here. No, ठीक है, 135 plus 45, 180, ठीक. So 135. So that is equal to, if you will calculate, I think it will come 5.7, 10 to the minus 24. Torque unit is force into distance, that is Newton into meter. Then what is the direction of the torque? Direction of torque. You see, this torque is equal to P cross E. P cross E. So this is the direction of P vector. This is the direction of E vector. So if we take the right hand thumbs rule, so keep the forefinger on the first vector, that is P. Rotate from P to E. So if we rotate from P to E, then thumb will give the direction of torque. So thumb will give the direction in which direction? Upward. Upward means it is represented by dot. So direction of torque is perpendicular and upward to board. And if the direction is upward, that means the dipole will rotate in which direction? Dipole will rotate in anti-clockwise direction. So here dipole will try to rotate in which direction? Anti-clockwise direction. So because the direction of the torque is upward and perpendicular to the board. Next, C bit. What is the net force? We know for dipole always net force is equal to 0 because two force. So here minus q will experience a force in opposite to that of P. So this is your F. So here plus q will experience force along the direction of P. So here two forces are equal and opposite. Both are acting on the system of dipole. So net force is equal to 0. Fourth bit, potential energy of the system. What is potential energy? Potential energy is equal to minus P dot E, that is minus P cos theta. So minus P is equal to 2 into 10 to the power 29. E is equal to, what is E? 5 into 10 to the power 5 into cos theta. Theta is equal to 135 degree. So if you will calculate, you will get 8.2 10 to the power minus 24. And since it is potential energy, energy unit is joule. So with this, I am concluding today's class. So if you are enjoying this video, so I repeat, you can share to your friends, because knowledge should be shared always. So in the next class, we will complete the chapter number 21. In the coming class, I will solve some more problems from the exercise. Okay, bye.